Hello, can you hear me? The slight intensity because of no power here, right? But I will back soon. Let's start the session. Can you hear me? Ah, the last week we discussed last week means that's before the last week. Right. We discussed the rotational motion. Can you tell me that point we stopped? I think I did the we discussed the angular that's a moment of inertia, the torque, and finally we discussed the angular momentum. Tell me that we discussed the angular momentum or not? I think we have to start from that point. All right, momentum and the torque. That means the angular momentum we already discussed now. I'm given the definition and how to write that L equals I omega. Oh, yeah, this is clear. Okay, this you need to know that. I mean, I'll discuss this thing. The angular momentum due to the rotation of a particle and angular momentum of a particle due to the translational motion. The both we can consider. First, I discussed the relationship between this angular momentum and the torque, and then we discuss how we write the angular momentum for a different bodies and different objects, and then we can discuss about the angular momentum conservation. Right, up to now we already know. Right. Up to now we already know that's these relations, right? That's I alpha that's equal to tau. It's a rotational form of Newton second law. We already know this, right? Then I discussed the angular momentum is equals to the I omega, and it is the moment of the linear momentum. That's the P into R. You can write as P is the linear momentum of the body. You can write as NBR. This thing you need to remember because if this the linear momentum and the radial direction they are having an angle, then you need to write this as a that's P sine theta or that's MV R sine theta. Angle also need to consider. I will come to that point again. Okay, then the relationship between this. The relationship between tau and L. This we need to discuss. Tau means as torque and the L means angular momentum, right? So we know that in linear motion, that if you apply the force on a body, the linear momentum is changed. That's the rate of change of the linear momentum we call the force according to Newton's second law. Similarly, here we can discuss, we can define that by applying a torque, you can change the angular momentum. If the body is moving about an axis with the angular velocity omega, by applying a torque, let's see this kind of body is rotating. If you apply the torque, means there's a small force you applied there. So then it's make a torque like this. Then the angular velocity will change. So it means that angular momentum is changed, right? So then we can define that angular, the rate of change of the angular momentum that's equals to the torque applied on this body. similarly to the translational motion, right? So we can write then so equals delta L over delta T. This is the relation between them. So equals delta L over delta T. The rate of change of the angular momentum that's equals to the torque applied on the system. Or a rigid body, you can consider any kind of body then, right? Okay. So right there. So to get the new. මෙහෙම ලියමු. දින්න නිතරම පොඩි මැසේජ් ටිකක් දෙන්න. සාමාන්‍ය පොඩක් මිනිත් එකෙන් ජොයින් මාරියෝ ආවා. Okay, we will write there. There's a relationship between the torque and the angular momentum. Then write them. In translatory motion, so okay, write there. In translatory motion, the force is defined as translatory motion. The force is defined as the rate of change of linear momentum. The rate of change of linear momentum. Likewise, in rotational motion, rate of change of linear momentum. Stop. And then likewise, in rotational motion, the torque or moment of the force, torque or moment of the force, torque or moment of the force is defined as the rate of change of the angular momentum. The rate of change of the angular momentum. See any body, any object like this, rotating about this, right? Applying a force F at the distance R here. Apply, then you can rotate like this body. The distance to this point, it says R, right? Right in this R. So the where is rotate it this point, you can take it as rotating in this path, and the velocity at this point, let's say the V, and mass of this point, let's say the M, right? For a small particle, we considering this, then the angular momentum of this particle, you can write angular momentum, it's L equals the linear momentum into r, v into r, into consider about the perpendicular direction, right? This velocity mv is the linear momentum. Here you can write that p equals mv. And by using this relation, this p r, this you can get the rate of change of this angular momentum delta L over delta t. And here r is a constant one, so then delta p over delta t is right in this format. Delta, right? As we know, this delta p over delta t, that's the change, the rate of the change of the linear momentum, right? Rate of change of linear momentum. That's equals to the force, right? Right in this side. So force is equals to the delta p over delta t. The force applied on a Newton second law. And then you can write this as delta L over delta t, the rate of change of the angular momentum. That's equal to force into distance. So this is the moment of the force. So it's called the torque. Clear? So this is torque or moment of the force. So we can take right. Therefore, we can say that torque is equal to the delta L over delta T. So it gives you that then the rate of change angular momentum is equal to the torque applied over body. Okay. You copy it down there. So this is important to you. Torque is equals to the rate of change of the angular momentum. Okay, you can write down. If you're going to understand, let me know. I'll explain again. හරිද? දැන් ඉවරද? Okay. Try to remember this, that O equals delta L over delta T. Right. Then we can get the relation that this, tau equals I alpha, also using this. So remember that how to get this. The thing that we considering this all the relations for a small the one particle, then we can write it for all the that's a rigid bodies, because for a single particle we know that the moment of inertia is mr square. But if you consider about the rigid body, you can consider it as a I. That's a moment of inertia. That's a different shape of bodies. They have in the different equations to calculate this moment of inertia. So then if you write the equation for a single body, you can consider that each of the body, each particle is consisted by this body, right? So you can write this all and then add together. Then there's a moment of inertia mr square, the sum of this all mr squares is become I. I is the moment of inertia. So for a rigid body, instead of mr square, we use get directly I, the value of I, then you can, right? Article එකට තමයි අපි සාමාන්‍ය explain කරන්නේ ගොඩක්. So and also you know that angular momentum is equals to the I omega. For constant I, the I the about axis we consider the moment of inertia is a constant for a body, right? So by taking the rate of change of the linear momentum, you can take that I as a constant. This is equals to delta omega over delta t, right? I you consider it as a constant. So we can write there. The I does not change with time. Therefore, you can write this delta L over delta T is the torque, and I delta omega over delta T, that's the rate of change of the angular momentum. That's angular velocity, sorry, that's equals to the acceleration, angular acceleration. So this relation also, we already know this relation, how to get this. We discuss and we did some example for this. And then you can write tau equals I alpha using this relation also, because of this delta L over delta T is a torque. එහෙමත් එතන නිකන් ලියාගන්න අපි කලින් I alpha කියලා ලියුවා. මේ විදිහට ගන්නත් පුළුවන්. So this is the Newton's second law, the rotational form of the Newton's second law, right? Okay, then right there. Very small topic. Right, the angular momentum of a rigid body due to translation and rotation both. Right, the angular momentum of a rigid body, angular momentum of a rigid body due to translation and rotation both. Due to translation and rotation both. Translation and rotation. Here I'm considering, let's say this XY axis, considering this axis, right? X, Y, and Z. And I consider the object there. Any shape of object is I'm drawing like this. So let's say it's moving to this direction with the velocity v, and also it is rotating about this axis, right? But axis here is also rotating the angular velocity omega, right? Angular velocity omega, it's rotating, and then translation motion both is there. Let's say the coordinate to this axis y. Here I'm considering that the object is that's like this. This is object is rotating and then moving like this. That's a normally rolling body. It's only like this, right? It's rotating and then moving, rotating and then moving. We know that's the wheel is that's a vehicle wheels are moving like this. It's rotating, and also it's make a translational motion also. It's clear? So in that kind of case, how we write the total angular momentum? This is because of this linear velocity. That's a linear momentum. So in the linear momentum, it's produce the angular momentum also about this axis we consider, it produces angular momentum too. And due to its rotation, it's already they're having the angular momentum also there. So then this sum of this or two, the both we need to consider to calculate the total angular momentum. So it's important, right? So we write there, they write there. Consider a body of mass simple m. Let's say simple m. Consider a body of mass simple m is rotating. Body of mass simple m is rotating with angular velocity omega. With angular velocity omega. Angular velocity omega. About point P. Here this omega, I'm considering the point P there, this point, right? About point P. As shown in the figure. About point P as shown in the figure. This point P, you can consider this as this is the, let's say this is the center of mass of the body, right? This point P is the center of mass of the body. Point P is the center of mass of the body. I will write there. This center of mass. This point is the center of mass. So it's rotating about the center of mass. Because it's easy to understand, because already you know that all the moment of inertia to write about the center of mass. And also now you know that how to calculate the moment of inertia about any axis, because we use the parallel axis theorem and the perpendicular axis theorem. We can calculate this. But here we consider that body is rotating and also translation motion is made. Right? So that's about the center of mass of the body. It's rotating with the velocity, angular velocity omega, and also it's make a linear motion because it's just like a rolling motion, as I mentioned before. Okay, then write there about the point P. And then write and the body translating, and body make a translational motion, and the body make a translational motion with a linear velocity v the body make a translational motion with the linear velocity v. Then you can draw this, right? Okay, draw and write then the angular momentum of this body. Then you can write the angular momentum of the body. That's the amount of, so that's L equals, that is that's angular momentum due to translational motion. Angular momentum is translation plus the angular momentum is rotation. Rotational motion, the what you can consider. Due to this, you are taking the angular momentum about the point over here, right? Due to this translational motion, then this side is as a linear momentum mv, and it's produce the moment as a p multiplied by this perpendicular distance, that's y. So then you can write there, this is equal to p dot y plus rotational motion is equal to, that's a moment of inertia of this body, consider I. So then, so right in there, this moment of inertia about the axis passing the center of mass, the moment of inertia is taken as I. So it's equal to I into omega. As I omega, you can write it. Right. So then L is equals to P equals to the mv y plus I omega. So you can write in the total angular momentum is due to this translation motion, it's also produce angular momentum, and due to its rotation, it's also produce angular. You need to consider both. That's the thing I'm about to discuss you. So when you write in this kind of question, it's important to get this angular momentum due to its translation motion also. Okay, you copy it down. Do you have any okay, which statement you need to repeat? I didn't see the chat. Okay, it's the, I'll tell you. Right there, they consider the body of mass simple m is rotating with the angular velocity omega about the point P as shown in the figure. That's P, where P is the center of mass of the body, right? And then right at the, and it's make a translational motion with the velocity, linear velocity v. Let's make a translation motion with the linear velocity v, and then write the this is defining the terms we used. Is it okay? The Ranisha will join it, right? We discussed only the relation between this angular momentum and the torque. So okay, that's, we can define that rate of change of the angular momentum is equals to the torque, right? So that's some given. If you have some doubt about this, ask me, then you can ask your friends to share the note, right? Give you a try. Again, it's a rate of change of the angular momentum that's equals to the torque applied on the field. So then we can say that the torque, that's easily we can say that this L equals the linear momentum into the distance, that's a perpendicular distance. So then delta L over delta T, we can write as delta P over delta T times R. So this is the torque, and this, how we get this torque, because this delta P over delta T is the force, and R is this, the force multiplied distance is the torque for moment of the force. That's why this delta L over delta T then equals to torque. If you are having any doubts, you can ask me. Okay. How to get the angular momentum How we calculate the angular momentum when there is a both translation and rotational motion. The body is moving like this. It's rotating, and then moving. This is normally the rolling body. Then the object, when you consider about the vehicle wheel, so wheel is rotating and also it's make a translation motion. In that kind of cases, you need to consider both angular momentum and the translational. That's angular momentum due to translation motion, because their momentum which make a moment of a momentum, right? Okay, you can write off this. If you don't understand, let me know. I will explain again, right? I'm always in that thing. If you finish the writing, let me know. Okay. By the wait for 10 or 20 minutes, then the power will be back, right? That's why it's a little dark here. Okay, then I'll give the example. Write down the example. Write down the find the angular momentum of a disk. Find the angular momentum of a disk. Find the angular momentum of a disk about the axis shown in the figure below. Shown in the figures below. In the following situations. Right. That's part A. I'll give you the figure. This is disk. So I'm considering different axes. That's why I'm again. So its center of mass is there. Axis passing through the center of mass and it's moving like this. The linear momentum, linear velocity, sorry, angular velocity about this axis passing through the center of mass is omega then. Right? You can consider this mass. So radius is r and the mass of this disk is m. You find the angular momentum for this first. Right? That's the direction of the angular momentum is also you can take in using the right hand corkscrew rule. You already know that how to get the direction of this omega. Right. And the second one I will give you. It's a different. You can draw this and then calculate. If we know the answer, you delete. This is the center of mass. Now I'm considering the axis which is passing from this point, but it's parallel to this axis passing through the center of mass. Right there, angular, that's omega is the angular velocity about this axis, not about this axis, right? And the distance to this axis from this point is equals to d. There radius is r and mass is m. You need to find the angular momentum of this system also. And see, now let's see, this is in XYZ plane. XYZ plane. And our disk is there. This is a disk. And it's rotating. That's clockwise direction. And the distance to this body, this is more, and also it's moving. The translational motion is has the velocity of v, and its omega is there. And the distance to this point from the axis, that's the center, you can write as d. Perpendicular distance That is center of mass. This body, right? And also you need this is the same disk. The radius is r and mass is l. And then the fourth, the part D, that is the case now. So okay, power is back. This is the axis. The same thing we are going to discuss here, but this omega is in the other side. Anti-clockwise is okay. Calculate this angular momentum of this system, and the radius is r and mass is. I think there there's 4 parts given in the same question, and go through it. Right. Import the way on. Itu sak nila may este. Ahora nave en la universidad. Dikali kaya na nage ni. Matatalo, matatalo. What is it? You got the money. So first one, here is moment of inertia about this axis is equal to the half mr square for a disk. For this, right? So then the angular momentum about this axis is equal to I omega. So you can write this as half m r star omega. This is the angular momentum of this system. And what is the direction of this angular momentum? It is rotating in this direction. It's a arm is directed towards upward. So it is, let's say x, y x, maybe y axis not maybe direction of the angular momentum is there. I'll put direction to get an idea. All right, angular momentum is in this direction. And the second one, here you know the angular momentum about this axis. Sorry, the moment of inertia about this axis. The psi equals half m square. But we are considering the angular momentum about this axis. Now we need to get the moment of inertia about this axis. So it's the moment of inertia about this axis is equal to the moment of inertia about the axis passing to the center of mass, because it's parallel to this center of mass. Axis passing to the center of mass plus the mass multiply the distance, square of the distance between. And this is, you know, that's half m r square. This is m a square. So the angular momentum is then I omega. You can write, because we given the omega about this axis. So that's half m r square m d square times omega. Clear? By simplifying, you can write this m omega over 2, you can take out. Here it is r square plus a 2d square. Yeah. In this case, the angular momentum is this. Here the angular momentum is a direction. It's also rotating about this. Its direction is up. Okay, clear? This is okay. Then this system here it's create angular momentum. That's it's rotating into this direction. It's create angular momentum into the board. And when this is moving to this direction, also it's moving angular momentum into the board. And then these two angular momentum due to translation and angular momentum due to rotation. The total angular momentum due to translation, and angular momentum due to rotation motion. Both you consider. For due to translation motion, that's a moment is mv, is multiplied by the distance, perpendicular distance is d. That's for a rotational motion, when it is rotating about this axis, this is I omega. I you can write as half m r square. So then m vd plus half m r square omega. So this is the total angular momentum in this system, and it's this angular momentum is into the vessel. If we put this cross and dot, means this is into the body. If you put this dot only, so then it's out of the board. So notation into the board and out of the board. So this angular momentum is into the board. I'll put that mark for indicating it's into the board. perpendicularly into the ball. And here the same thing, but only the different directions. And this produces angular momentum out of the ball. And due to the linear motion, it produces angular momentum into the ball. So then there are two directions. So here the angular momentum, that's MVD is not plus, then it should be minus, right? So it's minus half M R square omega. Because that's I'm writing this MVD minus this one. So I will tell it like this into the board. If you write this half M R square omega minus MVD, then it's out of. It's clear. I need to explain again. එතනදී මේ දෙන්නගේ මෙයාගෙන් එන මොමන්ට් එක තමයි half m r square angular momentum එක that's into omega. Linear motion again අනිත් පැත්තට. Produce angular momentum omega මෙහෙට and produce angular momentum into taking in and so we need to abstract this. Think about the direction. Right. Is it clear? Paul? හරිද? තේරුණාද? Hello. Hello. දැන් ඉවර නම් කියන්න. I understand. Because this rotate anti-clockwise direction and it's moving due to its translational motion, it produces angular momentum in the clockwise direction. So they both different directions, so we need to put negative sign there. But in this case, this moving to clockwise and also it produced due to the translational motion, it produced the angular momentum in the clockwise direction. So then both are in same direction, so they add together. Okay. I'll raise the board then. I'll give another question. Right there, calculate the angular momentum of Earth rotation, the Earth motion. Right there, the question, right? Calculate the angular momentum of the Earth motion. I'll give some data. The angular momentum of Earth motion. Okay, then take this data. The mass of the Earth, 6 into 10 to the 24 kilograms. Mass of the Earth is 6 into 10 to the 24 kilograms. and the radius of the Earth 6,400 kilometers. Mass of the Earth into 10 to the 24 kilogram. The radius of the Earth 6,400 kilometers. Then the average distance between the mean distance between the Earth and the Sun is the, let's say, the average distance between the Earth and Sun. That's called the astronomical unit. That's 1.5 into 10 to the 11 meters. 1.5 into 10 to the 11. This is the average distance between the Earth and the Sun. Center to center distance, right? Okay, that's a time period. That's for Earth rotation is 24 hours. Like you have to know this thing, right? That's a time period about that's of the Earth about the Sun. The revolution about the Sun is 365 years. Sorry, 1 year. That is 365 days. They go now. You need to know that. Remember. And also you need to know this Earth is tilted. The angle, tilting angle of the Earth is 22.5 degrees. You can consider that 23.5 degrees, right? The tilting angle of the Earth is 23.5 degrees. You got to know. Draw the picture. Figure this is Sun. I don't know completely. Earth. Earth is rotate anyway angle level. So it's 23.5 degrees. 23.5 degrees, right? Take a minimum axis rotate. So the Sun about the Sun is moving in this. And calculate the values to the power calculate. I'll have to expect this is let's see the omega 1 on omega 2 angular velocities. Calculation answer the first you need to get that's the angular momentum due to the rotation of the Earth about its axis, right? So I'll consider the first one, this angular momentum due to the rotation about its axis. The rotation of Earth about its axis. Right? So that's called the L rotation. It's LR, right? Due to rotation. Line is L due to its rotation. And then you can write as Earth is a sphere. The sphere, the moment of inertia of the sphere is solid sphere is 205 m/r square. The mass of this Earth is the length that is in I omega. So omega here is omega 1 input. That is 205 m/r square. This omega 1. This omega 1 you can write here. I'm writing this. Omega 1 is 2 over time period. That's it, T1. This is 2 over 24 hours. 24 hours. That 24 multiplied by 3600 to convert it to seconds. So then the omega 1 is right. So I simplify this, you can calculate the omega 1. Right. So I'll give this answer. (7.27 into 10 to the minus 5 radians per second). It's the angular, this value here. Now you can substitute and calculate this. That 205, m is 6 into 10 to the 24, and the 6,400 into 10 to the 3 kilometers in the meter. That's square of that. And omega 1 is, that is 7.27 into 10 to the minus 5. So then you can get the value for angular momentum of the rotation of the Earth. This is not the total angular momentum, right? This is the angular momentum of the rotation about this axis of the Earth rotation, right? This is simplifying this. No, wherever you can now, approximately you can see that 7.1 into 10 to the 23. Right? The unit is as kilogram star meter per second. The angular momentum of the Earth rotation about this axis. It's clear? We can calculate contain mummy taking spin කරන්නේ දැන් වෙන මොන හරි object you consider the same thing you need to do. It's clear. Then let's see the angular momentum. What's the orbit? Orbital angular momentum, that is when the Earth is orbiting around the Sun, it's also, it has an angle because it's make a rotational motion. It's considered another kind of rotational, that's orbital motion, right? So then this omega 2 you can write this equals to 2 over t2, it's 1 year about the orbital sun වටයක් හැද stake 1 year, that is 365 into 24 into 3600 seconds. 365 days and 24 hours into 365 25. 24 is that's much of hours. I multiply by 3600 to calculate seconds. It's a time period. It's 1 year. And that time period approximately 2 into 10 to the minus 7 seconds. Radians, sorry, radians per second. 1.99 in that's I'm taking as 2. Then you can write the angular momentum associated with the orbital motion of the Earth about the Sun. Can I erase this one? Hidden. Yeah. Deliver can okay. මේ data ටික මට දාන්න මම මෙතන ආපු වැලියු එක මෙතන ලියලා තියෙන answer rotation that's equals to the 7.1 into 10 to the 23 star meter. Okay, then second part the angular momentum, right? Angular momentum associated with the orbital motion of the Earth. Angular momentum associated with orbital angular momentum associated with the orbital motion about the Sun. Orbital motion of Earth about the Sun. Right? Yes, there are two to consider about. Okay, then this orbital I2 omega 2, let's say the different on that. The I2, the I is now is moving about this axis. Now you need to consider it's not moving about its axis passing through its center of mass now. Now it's somewhere here, the distance, let's say from here to here. Using parallel axis theorem, you can get this new I, right? So you need to write that one. This is actually you don't even, here that's when you consider about the Earth is rotating about the Sun. Earth you can consider as a particle, right? In this system, Earth is a particle. So then the particle is moving or rotating about an axis, right? That's a particle as m is the distance r. You can write as m r. Here, the similarly you can write that. So is this particle actually consider the particle is rotating about this. So you can write it as I equals this m d square multiplied by omega 2. So m is 6 into 10 to the 24 is the mass of Earth. D is the distance between this 1.5 into 10 to the 11. The square of that. Omega 2 is 2 into 10 to the minus 7. Okay, by simplifying this, you can get that. This will produce as approximately 2.7 into 10 to the 40 kilogram star meter per second. Now there are two angular momenta. This one and this one. Now these two having this is in this direction, and this one is tilted with the angle 23.5. You need to consider about the total angular momentum. The resultant of these two you need to consider. When you get a resultant as a vector addition, you need to add these together, right? So that's what I want to tell you. I'll erase this solve now. There are two angular momenta. That's one is in this direction, another is in this direction. This is orbital one. This is rotational. The angle is 23.5 degrees. You want to get that net angular momentum, that's equals to the that's L orbital square of that plus L rotation square of that plus 2 L orbit into L rotation into cos 23.5 degrees and a square root of this. You don't need to simplify this. If you want to write it, that's the result and we get. That's this is p square plus q square plus 2pk cos theta, like that. Get the vector sum because of they are having an angle between. That's if there is a true angular momentum, you need to get the result according to the vector addition. Because this the angular momentum is a vector, you need to consider the vector addition. හරි නේද ඔයගොල්ලන් මං හිතනවා ඒක තේරුම් ගන්න පුළුවන් ඇති කියලා. Okay, another question related to this angular momentum, and then we next part we'll discuss the rotational kinetic energy and the other rotational the parameters related to this rotational motion. And after finally we discuss the angular momentum conservation about this rotational motion. Then after I will come back to the circular motion and some applications of the horizontal and vertical circular motion. Then the session will be finished, right? Okay. Right there. Question, right? A particle of mass simple m is a particle of mass simple m. Particle of mass simple m is released from a point capital P, a point capital P at x equals symbol x naught might be x equals symbol x naught on the x-axis, from origin capital O, from origin capital O, I figured out, and falls vertically along the y-axis, falls vertically along the y-axis, as shown in the figure. Okay. then write the first part of the question. මේ විදිහට වැටෙනවා එහෙම හරි. So given එක එකක් දෙන්න මෙයා දැන් මේ Q වගේ point එකකට yeah after time T naught and Q it is the question. So write the first part. Find the torque acting on the particle. Find the torque acting on the particle at a time simple T naught. At the time simple T naught when it is at point Q. That time T equals 0 is that time T equals 0. Find the torque acting on the particle at the time T naught when it is at the point Q with respect to capital O. With respect to capital O. With respect to capital O means you need to consider all the things related to this O. The rotation axis is passes to O like that. The second part of the question, problem number 2, find the angular momentum of the particle. Find the angular momentum of the particle about capital O at this time C naught. At this time T naught. Okay, I will repeat the question. First part, find the torque acting on the particle. Find the torque acting on the particle at a time T naught when it is at a point Q. Find the torque acting on the particle at the time T naught when it is at point Q with respect to O. With respect to O. The second part, find the angular momentum of the particle about capital O. Find the angular momentum of the particle about capital O at this time T naught. At this time T naught. And then third part of the question, show that the tau equals delta L over delta T in this example. So that tau equals delta L over delta T in this example. I think you can do it. Go through it until 5%. Okay. Okay, let's see. All right, let's see how to do it. So, what is the torque? How the torque is applied? That's about this point. The torque. Uh, let's distance. Let's say r. You can write it in this figure. The r equals if this is theta, right? Yes. When you write r, the torque is the moment of force. Torque is equals to the force multiplied by the perpendicular distance to the line of action. This is the perpendicular distance, it's not. The force is a mg, the weight apply the torque, mg x naught. The second, the angular momentum, L. Angular momentum is equals to the I omega. Here this you can write it's a linear momentum, it's moment of the linear with the PR. That's linear momentum to this direction. That's the velocity at this point. You can write this is mvr, and v you can write using v equals u plus 80 downward. So v equals the 0 plus t naught. After time t naught they ask you. So that's the way that you can substitute there. M t naught. R is the distance from here to here, that is x. This is the angular momentum after time t naught. And third one, that's delta L over delta t. That's equals to this m delta change in momentum is initially it's 0 mg t naught x. This divided by the time taken t naught. Let's cancel this mg x naught actually, sorry. And that's equals to the from first one mg x naught equal to. So we can write this term. So then delta L over delta t, that's equals to 2. Clear? Clear? What is it? All right. Okay, then revise this. Write the rotational kinetic energy. rotational kinetic energy. Rotational kinetic energy. How to write the energy, kinetic energy? Uh, I consider the plane like this, and then axis. I rotate this axis about this plane. I rotate about this axis with the angular omega. Let's consider on this plane there are different particles at different distances. One particle. All the directions they are having particle like consists of some particles, right? Let's see the masses are like M1, M2, M3, M4, and up to Mn. Right. The distances with respect to this R1, R2, R3, R4, and Rn. These are the distances about this point. First you write. What is very what very hello, it's about 0.0, right? So then the linear velocities in this direction is v1, this one is v2, and this v3. It's a tangential velocity. v4 and this v, and let's the moving in the rotation. When we should rotate this, we're moving like this kind of different circles. Okay, then right there, consider an object. Consider an object rotating about an axis. Consider an object or body rotating about an axis through a fixed point capital O, on the object with a uniform angular velocity omega. With a uniform angular velocity omega. Okay. Let particles of masses m1, particles of masses m1, m2, t, blah blah blah, then mn, m1, m2, so on. There's mn situated at the distances, situated or located at the distances. The distances r1, r2, blah blah blah, and rn. Respectively. Respectively from the point capital O. From point capital O. Point capital O. Be moving with velocity. Be moving with the tangential velocity. Moving with tangential velocities V1, V2, that's Vn. V1, V2, and Vn respectively. Respectively, right? You can draw the diagram. This is the point of omega. Plane this. All the objects I'm considering on this plane. Other party Mandina plane different particles on this plane I'm considering. Yeah, like this. Okay, this. This is R1, R2, R3, 4, and R8. Linear velocities, velocity V1 here, V2, V3, and like this. So rotating. Like this different one, you can get the they're making a circular motions like this, different circles. I'm not going to draw this. You can draw this one. And then total that's the rotational kinetic energy of the system is the sum of all the kinetic energies of these all the particles in the system. This object over, right? You have right there the rotational kinetic energy. Of the object equals to the sum of all kinetic energy of the particles on the body, on the object. Having their individual linear motions, you can say that. So this rotational kinetic energy I'm writing is E. In later you can use. Right, use E. That's a single particle. They're having the kinetic energy of m1 v1 square plus m2 v2 square. So then finally half v n vn square. It's a rotational kinetic total. But we know that the tangential velocity v1 equals r1 omega. So omega is same for all because it's the same body is rotating omega. And v2 you can write that's r2 omega so on. So substitute in there. So I will write some there. You can write as half m1 r1 omega, that's square of that. Half m2 that's r2 omega star of that. Half mn rn omega square. So omega square and half is common for this all. You can take those out. You can write then take half out and omega is m1 so the r1 is m2 r2 is final term you can write this mn or n. Then omega is take out from the other side. We know this m1 r1 is plus m2 r2 is plus blah blah up to mn rn is it is the and there's a moment of inertia of a system of particles in this object. Now this is the moment of inertia of the object. We consider about the rigid body is the moment of inertia of that rigid body. So you can write in the rotational kinetic energy is half I omega square. So its I is corresponding term, that's a quantity for the mass. So then it is just like a half mv square. Here rotational kinetic energy is that same like that's I omega square, half I omega square. Translational we can write is a half mv square. So here it is half I omega square. So similarly, you can use those equations. Setting up to now. Right, let me know, then I'll finish the writing. Again, method level was episode. Are you makan that we can write then this E I'm writing here. That's E equals rotation kinetic energy is half this one we can write as a sum sigma I equals 1 to n mi ri star. So in short form we can write like this omega square. So here the I equals this sum of all the moment of inertia of individual particles, that is mi ri square. So it is the moment of inertia of the system or the object. Of the object about the axis passing through the capital O. Next up, about the axis of rotation. Therefore, you can write that rotational kinetic energy is equal to half I omega. So this is the equation for rotational kinetic energy. Okay, write this half I omega square similar to half mv square. You can different shape of the body, the I will be shape different. So then you can calculate this rotational kinetic energy of any system. And also you need to remember that if the body is rolling, rolling means that's both the rotation and the translation is there. So you can write the total kinetic energy is equals to the sum of the translation and the rotational kinetic energies of the system. I'll give that point. If you finish writing this, let me know. To write that kinetic energy due to translation and rotation both. That's kinetic energy due to translation and rotation both. Translation and rotation both. This kind of this is rotating and then also move. Mass of it is, let's say, the moment of inertia about this one is, let's say, I better than so then write the consider a rotating body. Consider a rotating body. Consider a rotating body which is translating with the velocity v. Is translating with a velocity v and rotating the angular velocity omega. Rotating with angular velocity omega. Total kinetic energy write the total kinetic energy of the body of kinetic energy, let's say the total that's equals to the translation of kinetic energy translation plus kinetic energy of rotation equals to half mass of this body, let's say m square plus half I omega square. Both you need to consider, right? This is the total kinetic energy of this kind of system. In this is rotating and translation both is there. You need to consider the both the energy. Okay, to that. Okay. It's rotational kinetic energy right now. That's then write the rotational work. You keep those in mind that kinetic angular momentum, rotational kinetic energy, the rotational work. Rotational work. Okay, I'll consider a body like this. Okay. Axis passes through this point. Make a rotation. The velocity, let's say omega. And when I rotate this about this point P here, this point P here, due to the rotation, let's say that point P, let's set the distance R, yeah, change to this point, this, and now point Q. Conductor and element, smaller and change I'm considering that's kind of, let's say let's say delta S. Let's do this way. Make angle theta here. Consider that angle as distance is R. The angle is delta theta. There, when I rotate this point P is moves to this to the point Q. Let's say I can say it's like at time t equals 0 here, and after time t equals t or delta t, let's say delta t is come to this point. Only point එක විතරයි ඇඳේ මේ object එකම rotate වෙනවා. ඒකට ඒක ආය අඳින්න ගියාම අමාරු වෙන මම ඇඳේ. So you can write there, consider a body is subjected to a, because whenever the thing is that this point will come to there under the force applied on it, right? Apply the force F on it. Let's say force no, tangentially you apply the force, right? It's important. And this point Q is right. The consider a body subjected to a force capital F. Body subjected to a force, subjected to a force capital F. Right, the body is subjected to a force capital F. Then right, suppose the body undergoes an angular displacement delta theta. Body undergoes an angular displacement delta theta due to the torque of force capital F. Due to the torque of force capital F. And then draw this and write the work done by the force. Work done by the torque. W equals force multiplied by the displacement. That's the PQ displacement here, P to Q. PQ displacement, right? So we're considering a small change because for a small change, it's linear. This path is linear. We can consider this path is linear. If not, this is curved one, so displacement and distance is little different. That's why for a small change, we consider this and then write it for all. Right? General equation we discussed. And this C equals to L multiplied by delta S. Of course, you know that the C equals R theta. So this can R times delta theta. Because this is C equals the C equals R delta theta. So this equals R theta. Then F into R is a torque. You know that the torque applied is this equals the force into the perpendicular distance. So in a fraction. So it's torque. So write that W equals a tau delta theta. So this is the rotational work. Work done by applying a torque. Like this. So tau equals F into R. Rotational work you can write tau into delta theta. If you know the torque and then you know the what is the angular displacement, it's make under the torque applied. So that's work done is the tau delta theta. Same way you can write that the power delivered by this torque, this work, the rate of the work done is the power. You need to divide this by the time there. Right? So delta T, if the angle is theta, it is tau theta. Actually, this is the work done. Okay, then after that we can write this power delivered by the torque. Power delivered by torque. Topic here is power delivered by torque. As we know, that's the work done is equals to the tau delta theta. It's a changing work done connected to delta theta. That's the rate of change of the work done. It's a power. So you divide by the time. So the rate of work done delta theta over delta t. So this is the power. So what is this? It's a angular velocity. That's the rate of change of the angular displacement. I'll erase this part. Right? In the power you can write tau omega. Power delivered by the tau is the tau omega. These equations are similar because that's a work done is tau theta or delta theta. Let's see. This work, this torque is corresponding to the force in rotational motion. Angular displacement corresponding linear displacement. That's the W equals F. And here also the power, the torque corresponding to the force and the omega corresponding to the velocity. So that's F equals F. Similarly, in rotational motion, you can use those in terms of angular quantities. That's power delivery is tau omega. In the angular velocity is omega, the power delivery is omega. And in this case, you need to know if the case, in the case we consider that the angular velocity is changed. So then the average angular velocity you need to consider for calculation of the power. The mean power divided. According to this, actually, we say that uh, by applying a torque, you can change the angular momentum of a body. Right? It's external torque applied on the body that should equal to the rate of angular momentum change. You can see. It's the power. And also we can define this, the impulse. So here, if you are applying a force at a distance from the axis of rotation, then also we can say that we can apply the angular impulse. That's very large torque applied for a small time interval. So we call it angular impulse. Mathematically, we can write it as we can prove it that the momentum change, angular momentum change is equal to the angular impulse applied on the body. Okay, I will erase this. Then write the next term is angular impulse. Angular impulse. Normally we use letter J for angular impulse. Considering like this, when you go bird, this is the hinge. The hinge කරලා තියෙනවා. L end තියෙනවා. පොඩි කරකෙන්න පුළුවන් විදිහට නට් එකක් දාලා තියෙනවා. I'll apply the force F on it at the distance R. පාර මෙහෙම පොඩි වයල් මොකද force එකක් දෙන්න එක. හා? ගාන මේක පාර පොඩ්ඩක් උඩට වෙන්න යනවනේ. පොඩි start point. That's the impulse. Again, that's the torque is not applied. The constant torque is not applied. At suddenly we apply the torque for a small time interval. So then its momentum will change. So it's angular velocity change. Then, so by applying impulse, then you can change the momentum, angular momentum of the body. First, right here, consider a rod. Consider a rod hinge. Consider a rod hinge at its one end. Hinge at its one end. At its one end. Right, hinge at its one end, as shown in the figure. As shown in the figure. Okay, then right, it is acted by an external force capital F. Is acted by an external force capital F for a time interval delta t. For a time interval delta t. As shown as shown. Right? You can draw this. You can draw it as shown. You can write that torque equals 3 into R. That is the torque applied. Right, then this torque equals to torque equals Fr. Okay. In the end, remember the rod starts rotating. The rod starts rotating about the hinge. The rod starts rotating about the hinge due to the torque. Due to the torque, that's torque equals Fr. That's right, due to the torque. Okay, then after that, write the product of torque with the duration of its exertion. The product of torque with the duration of its exertion is called the angular impulse. The product of torque with the duration of its exertion is called angular impulse. Then you can write this angular impulse equals the torque into the time. Time interval, or like this, torque is J, that's angular impulse, torque is tau to delta T. And write that. It's a vector quantity, right? The vector quantity, direction of the angular impulse is the same as the direction of the torque. As we know that the tau equals delta L over delta T, the rate of change of the angular moment, right? So it's produced with that so J angular impulse, that's equals to delta L over delta T times delta. Then this delta T cancel, and then the angular impulse is equals to the change in angular momentum, right? So this we can say angular impulse is equals to the change in angular momentum. Angular impulse equals to change in angular momentum. Similar to the translational motion, as a impulse equals to the change in linear momentum. So it's giving you that when you apply the torque, you can change the angular momentum. Okay, I'll erase this. All right. Tonight the conservation principle of conservation of angular momentum. At this point, let's stop the class for today. So let's write this principle of angular conservation, right? Let's write the topic then principle of conservation of angular momentum. Principle of conservation of angular momentum. Principle of conservation of angular momentum. But it gives you that we know that the external torque applied on the body that's equals to the rate of change of the angular momentum. If it's external torque, this is external torque that's equals to 0, then what happens? Then this rate of change of the momentum 0. So it gives that change in momentum is 0. So change in momentum is 0 means that the angular momentum should be a constant. It's a constant. So it's a constant means that's the initial angular momentum that's equals to the final angular momentum, right? That's some right into I that's equals to L F there. This frequency. So which is called the angular momentum conservation. That's as a law we can say like that's if there is no any external torque applied, so the total angular momentum of the system remains unchanged or remains constant. So they write there. It's supposed to write the principle and then come to this point. Let's write. Then write there when no external torque when no external torque acts on the system, then no external torque acts on a system, the total angular momentum of the system, remains constant. Remains constant. It's for isolated system, right? All the conservation laws true for isolated. What do you mean isolated system means there are no any other effects from the external effects from the other system. Kind of not system considered, no any other influence. Okay, then can write this. It's tau equals delta L over H. If tau equals 0, then this rate of change of the moment angular momentum is 0. Then the change in angular momentum should be 0, and it gives you the angular momentum is constant. So that means the initial and final angular momentums are equal. Momentum. And further we can write this initially, let's say the omega 1 and I1. Final system has I write this in different way. This is omega I and I1 omega 1 is greater. 1 omega 1, that's I2 omega 2. Two cases you consider. You can consider total angular momentum. I1 omega 1, this I2 omega 2. Okay, is it clear? Finish writing. Hariද? Tamaliya? Right. Right example. And these applications of this angular momentum, principle of angular momentum, we'll discuss next week. Right, that's part. And but here discussing on one question example. Then the part we'll discuss in next week, right? So then we can do more questions. I will give the next tutorial related to this rotational dynamics. Then write an example. Consider a disk of mass capital M. Consider a disk of mass capital M and radius capital R. And radius capital R is rotating with angular velocity omega. Is rotating with angular velocity omega about its geometrical axis. About its geometrical axis as shown in the figure. As shown in the figure. Okay, then write a small object of mass simple m. A small object of mass simple m falls gently. A small object of mass simple m falls gently on the edge of the disk. On the edge of the disk. The edge of the disk and stick to it. And stick to it. Find then the angular velocity of the disk. Find the angular velocity of the disk. This small object is fall on it. See there? Angular velocity is changed. For this small mass, let's see resistance to the eyes. So this is initial system now. It's a final. Final means that's after the mass fall on it. There's no any torque applied on this system. The rotating thing, there's some object will stick and drop it on and we stick on. Right? So usually this angular the moment of inertia about this axis is this is half m r star on angular velocity is omega. And this system now the I2 is half mr star plus the angular, so the moment of inertia of this particle is then mr star. Omega, so omega dash we need to find. And here, since there is no torque, there is no external torque, on the disk, there's no torque on the disk, then you can say that initial angular momentum should equal to the final angular. That's I1 omega 1 is equal to I2 omega 2. So way you can do this. Angular velocity we need to find, right? Not the angular momentum, because according to the angular momentum conservation, they say initial angular momentum that's equals to final one. So you don't need to find it, because if you write the initial one, that's the angular momentum of the final system. There is no torque applied on it, right? Here, since there is no external torque on the system, then we can say according to the angular momentum conservation, it's initial angular momentum that should equal the final angular momentum, right? So it's on omega 1, I2 omega 2. Now these corresponding values you can substitute and get the answer. Most common questions the examinations also they can ask. This I1 is half mr square, omega 1 is omega, I2 is now half mr. That's the important thing, is that you need to get the moment of inertia about the axis of rotation when you write in this. That's why we, before come to this point, we discuss about the moment of inertia, torque and everything. Now we not know how to write those. So r star will cancel. So then the omega dash equals to the, this is m and half can divide, you can multiply it by 2 also. This m and the 2n on m plus 2m. M omega. It's omega is there. M omega divided by m plus 2n. So this is the angular velocity after the small mass m stick on the edge of the disk when it's rotating with the angular velocity omega. There are many applications related to this angular momentum conservation. So I will discuss those in next week. I will stop the class from this point today. If you have any questions, any doubts, you can ask. I stop the class from this point, right? Do you have any questions? No. Okay then. Good night. God bless. If you finish writing anything, you can leave, right?